Hello everyone, my name is Kamal Kashyap, and today I'm here presenting my final year project with in on behalf of my team, and my project ID is 2021CSEPID15. So I'm presenting my project, which is titled as Neural Approach to Survival Analysis with Interval-Censored Observation using Deep Learning Models. So starting with the need and use of this project in real world problems, especially in healthcare sector, manufacturing, and business analytics, we often want to predict how long it will take for an event to happen. Like if we say, for an example, we want to know the survival time of an any patient, and if we talk about in healthcare sector, so this could be the time, until a patient relapses, a machine fails, or a user stop using an app. But here we are more focusing on in healthcare sector, so we will only talking about patients and the machines and the medicines here. But here's the problem: we don't always know the exact time something happened. We only know that it occurred between two observations. Okay, for example, two doctor's visit, and this is known as interval censored survival data. And the most traditional models can't handle this well. For example, Cox model. If we talk about traditional ways, so the Cox model is the model that is being used for such things, or basic AFT models as well. Assume that either the event time is known or that at least right censored, but they struggle when the exact timing is hidden inside a time range. On the top of that, these models assume simple linear relationships between variables, which doesn't match the complexity of real world data. So this is actual the problem is, and what we are proposing as a solution is to solve this. We built a neural AFT model using deep learning, and some of its features, if I tell you, is that it predicts survival time directly from features without using without needing the exact event time, and it used a neural network to capture non-linear pattern that traditional methods miss. And it also support interval sensor data, making it applicable to real world cases like patient tracking and maintenance schedules. So this is our literature survey and all this, and here comes the problem statement, as you can see, and this is a proposed model, as I've explained. So coming to the workflow of our project, here it is. So first, what we are doing is we are processing our data, and then based on some architecture, we are modeling it, and then we are training our data based on some applications, based on some libraries, and then we are comparing it with some traditional models and validating it. And after that, we are measuring the risk based on some features, and then we are testing it. And after that, the main thing comes that to deploy our model, uh, for which can be used as an invention in the future. So this is our workflow, this is how our project is working and everything. And these are the use cases, as I've told that we are more focused on healthcare sector. So as you can see here, there's healthcare and clinical trials, pharmaceutical drug testing, predictive maintenance in industry, and bioinformatics. And what makes our project unique and what is the novelty of it is, first of its kind, deep learning framework for interval censored. Basically, there is not a single model that is right now working on neural network or using deep learning model. Okay, and yeah, you can see here extensive synthetic plus real data evaluation pipeline and everything here. These are the dependencies that what we are using is Python. It is the whole project is built on Python, and we are using the core libraries of Python, that is NumPy, Pandas, scikit-learn, and SkyPy. Sorry, and deep learning model, we are using core libraries, that is TensorFlow and Keras. And coming back to the visualization, we are using Matplotlib for our graphs and Seaborn. Experimentation and evaluation, we are using TQDM, JobLib, and TensorBoard. And for generating the data, we are using SkyPy and NumPy.random. Okay, so this is our flowchart. This flowchart of the project. From starting, we are inputting the data, providing the data set, and then we are just evaluating it on this on some basis, and then we are designing a neural network using the AFT model, and then we are training it, and or basis on the basis of some libraries, we are evaluating it and optimizing it. After that, we are comparing it with the traditional models, as I've said earlier, and then after that, we are trying to propagate the risks. So after that, all if the performance of our model is accepted, then the model will be deployed, and if not, then it will again train the data, get all the data set and all the things until the everything is satisfied. It will go on. Here I've also input some of our screenshots of the model, working model. I've also mentioned the graphs as well, everything. Here is the references of our project, and that's it. So this is all, and now I am moving forward to the working model, the coding part of our project. So here it is. As you can see that I have run it before, and here the data is training the epoch and everything. So epoch is a whole cycle, you can see. Also, I want to show some things like, as you can see here, this is the graph. Okay, so what we are doing, let me tell you some of the major terms that we are using here is, first of all, that is mean survival. So what is mean survival? It is the average time until the event of interest occur, for example death or failure, etc. Training loss, error of training data, and validation loss, error of unseen, that is also validation data. So if we talk about the graph, if we talk about graph here, so you can see the training loss is indicated with the blue line, and the blue line is so much messy here. So what is actually means is, it is not in its ideal behavior. The ideal behavior of training loss is it should decrease steadily, and just like you see, you can see this validation loss, it must be a curve like and a straight curve like a line, but it's not. So our training data is not good. Okay, that's not in its ideal behavior. And the orange line you can see here is validation loss, and its ideal behavior is it's also decrease, but may flatten or rise in overfitting. So but you can see is it's also decreasing, so it is okay. The validation loss of our data is okay, but the training loss is not okay. So our model right now is not good. Why not good? Because the data set we have provided is not good enough, so we have to provide more good enough data. Okay, this is based on some of the implications, but if let's talk about here. So here you can see is predicted survival time, and actual versus predicted survival time, and it is the actual survival time. So you can see here we are comparing both of the terms on the basis of some of the factors, and what is the actual survival time of any event, and what is the survival time we have predicted from our model. As you can see previously that our uh, training loss data is not good, so that's why the predicted survival time of that event is also not good. Okay, in relation with the actual survival time. So I am running this project again. We will give a command python train.py, and we will run it. So you can see here our model is going to train again on the basis of the data set we've been provided it, and here it is training the model, the epochs. And also if you want to see that, you can see here the loss and validation loss of all single data set we have provided it. We have taken data set of 100 models, so you can see here again that our training loss and the validation loss, as I've simplified them earlier as well. And here the predicted survival time. We can also get output for a single person if we provided all its reports and everything, enough data to train our model and work on a good manner. So this is it. And yeah, as you can see here, we have using TensorFlow for grid search, and that is an actually deep learning library, and pandas and TensorFlow for our data. And here numpy, you can see everything. And this is the csv file for our raw data, and this is our process data we have provided. Okay, that's it. Thank you.